I'm going to start by looking at a problem that you guys may have seen last year in 20-1. Okay, this is a maximization problem. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, does anyone remember questions like this from 20-1? A little bit from quadratics? Ringing a bell somewhat? Maybe? No? Okay, well, we're going to look at we're going to review how did we do this in 20-1? What tools did we have to solve this type of problem in 20-1? I gave this question to my 20-1 class like at the beginning of the semester. And then we're going to revisit it through the use of derivatives. Okay, so we have to start out the same way. What do you think would be a good thing to do to start this problem? Yeah, draw it. Okay, so we've got a river. And then we want to make a rectangular field that borders the river. And we want to fence it in. Okay, so we don't need to put any fence along the river. I think this is what's called a natural barrier, if you've ever heard of those. I went to a zoo in the Netherlands that has no fences but natural barriers. So you can you're standing and then there's like a moat and then you see lions on the other side. And it's a little bit frightening, to be honest. But I suppose that's what this would be. And so you have this river here, and then the rest of this is all fencing. Okay, so this is a rectangle. Rectangle has two dimensions. It's got a length and a width. And this is also the width. Okay, so what we want to do now is, now that we've got these two dimensions, length and width, we want to try and come up with a relationship between the two variables. Okay, so what other information do we have in here? What else do we know that we haven't used yet?
We only get 2,400 feet of fence.
Right, we only have 2,400 feet of fence. And that would be the perimeter that we have available to us to make this fence, right? So that would be the sum of these three sides. Okay, so the perimeter is going to be 2 widths plus a length. And that perimeter is 2,400. Okay. Now what we want to maximize here is the area. And area is length times width. Now, we can't think about maximizing this yet because we have 1, 2, 3 variables, and that's too many. So what we need to do is use this piece, which is kind of like a constraint, to reduce this area relationship down to 2 variables instead of 3. Okay? So what I can do is I can maybe express length in terms of width. If I isolate length here, right, I can say, okay, well, length has to be equal to 2,400 minus 2w. Okay? And then I can do a substitution. I can take this and sub it in here. And now I have an equation that relates the area to the width, and I only have one variable. Oh, whoops, sorry. Oh yeah, that's right. 2,400 minus 2 width times the width. Okay, because this is the expression that is equal to width. Okay, and I could expand that if I want. And what I'm going to see when I expand, I get 2,400 w minus 2w squared. And that is a quadratic function, which makes sense, right? If you're thinking about area, you're multiplying two things together, it's going to be a quadratic function. So negative 2w squared plus 2400 w. Okay? So in Math 31 and in Math 20-1, up to here would be the same. You'd have to do this point. Okay? Now in 20-1, if we wanted to find the max point of a quadratic function, algebraically, without graphing it using technology, the only way to do that is to transform this function into vertex form by completing the square, right? And once we have the coordinates of the vertex, we know what the maximum value of the function is, and we know the value of w that makes that maximum value possible. So in 20-1, if we wanted to solve this using the tools that we have in that course, to find the maximum area, we would need to complete the square to convert to vertex form. Okay, so let's do that. I want to do it so that I can remind you how painful it is, so that you can appreciate how beautiful it is to do this with derivatives. Okay? All right, so when we're completing the square, okay, the first thing we need to do is to factor out the coefficient of the variable squared term, which is the w squared term in this case, from the first two terms. So we're going to factor out the negative 2. So this is going to be equal to negative 2 times w squared minus 1200 w. Okay? Does anyone remember what we do next? If you don't, that's okay. I know it's been a while. No? Okay. So what we want to do is we essentially want to make this guy into a perfect square trinomial. Okay? So what we need to do that is we need to take half of the coefficient of the coefficient of w. Half of that is negative 600, and square it. So negative 600 squared is, I don't know, 36 with 4 zeros. What is that? 360,000? Okay, there we go. So if we want this to be a perfect square trinomial, it would be this. Plus 3,600, or sorry, no, 4 zeros. There we go. There we go, right? So if I just close that off there, this would now be w minus 600 all squared. And that's a perfect square, okay? But I can't do that because what I've just done is I've just added 360,000 to this bracket. I'm not allowed to do that. So to compensate, I'm also at the same time going to subtract the same amount. Okay, now all that I've done is I've basically added 0. That's all I've done. Okay? All right, so the next thing I'm going to do is I want to take this last term out of the bracket because I don't actually want it in there. I want it to be a perfect square trinomial because then I'm actually doing this process of completing a square. I'm making a perfect square trinomial, okay? So if I take this out, I can't just take it out because I'm actually multiplying it by negative 2. So I've got to do that distribution as well. and then minus 2 times negative 36, or 3, why do I keep saying 36? 360,000. There we go. Okay, so that's how I would remove that last term from the bracket. I have to distribute that multiplication of negative 2. Okay, now I can kind of simplify a little bit. This can now be factored. This is now a perfect square trinomial. This is now negative 2 times w minus 600 squared. And this becomes plus 720,000. Okay, now this is in vertex form. So if I wanted to graph this, which I do, okay, here's what I know about it. I know that it is a parabola, and the x-coordinate of the vertex is 600. The y-coordinate of the vertex is 720,000. Okay, and this thing actually points down or opens down because the a value is negative. Okay, and if I wanted to go even further, I could even go way back up here and think about this form. Well, actually, I would go a little bit more like this. Okay, if I think about what this would look like factored, right? I haven't actually factored it here, but it would be 2w times w minus 1200 factored, if that makes sense, right? So if I wanted to get even more accurate, for the purpose of this question, I don't need to do that. I could also plot the zeros, the x-intercepts. One of them would be at 0, and the other one would be at 1200. And then this is going to look like this. And of course, can't go below that because this represents a width and this represents an area. So this is sort of a restricted domain. Okay. So using the knowledge from 20-1, we'd have to switch this into vertex form by completing the square. Now we know the coordinates of the vertex. We know that this thing opens down, so therefore it's a maximum. And the y value of the vertex is the maximum value of the function, and that represents the area. So therefore, the max area is 720,000 feet squared. Okay, what is the width that makes that area possible? 600, because it's the, yeah, it's, there you go, yep. The width equals 600 feet, and the length is what is it? 24, wait, where is the width? It's here, 2400 minus 2w. So the width is 2400 minus 2 times 600, which is 1200 feet. There we go. So this is everything that we need to know. Okay? All right, so far so good? Yeah, nice little review of completing the square, hopefully. That's good to know in case you ever have to graph a parabola by hand. which you might if your graphing calculator's taken away from you. Okay, let's talk about how to speed this up a little bit, because now we know about derivatives. And we know that when you're at a maximum point on a function, what is the value of the derivative of that point? What is the value of the derivative over here? 0. Exactly. So using derivatives, okay, we still have to get to this point. A equals negative 2w squared plus 2400w. We still need that. But all we need to know is we need to know what is the value of the width when the derivative of the area is 0. That's it. To get the maximum area, we just need to know what's the width when the derivative is 0. Okay, so or max area, what's W when A prime equals 0? Because when A prime equals 0, the original function is either at a maximum or a minimum. Okay, so all we need to do is find the derivative of this thing. A prime is going to be negative 4w plus 2400. If we set that equal to 0, we're going to get 4w equals 2400, which means w equals 600. That's it. No need to complete the square. Okay, once you have the width, you can figure out the length, because the length equals 2400 minus 2 times the width, which is 1200. And then to get the max area, you just multiply the two together. Okay? Any questions with that? No. Okay, so one thing that I talk about in all my math courses is categorizing problems, categorizing the question, or diagnosing the question. Sometimes I use that wording. If one diagnosis of a type of max-min problem is that it is a quadratic function, that it turns into sort of a quadratic max-min problem, right? So it's going to turn into that 20-1 type problem, okay? We're going to look at others, though. They don't all become parabolic, and we'll see that in a second. Another one that we're going to look at in a couple minutes, and this is one that comes up quite frequently, is that we rely on Pythagorean Theorem, right? And then we're going to get a radical because we have to take the square root to determine one of the sides. Okay, and one thing I'll say now, and I'll say it again as we keep doing these, is that this unit can seem a little daunting. You might see me do a problem and be like, oh my gosh, I'm never going to be able to come up with that myself. And what I would say to that is that if you expose yourself to lots of different problems, and practice them, there's only so many ways that we can ask these types of problems. Okay, so if you just practice, it's like you're not going to be surprised after a while, if that makes sense. Okay, but I know it can seem overwhelming at first. And if you see me do something or we do something together and you're like, I would have no idea where to start, that's fine. That's kind of where you should be right now. As long as you can follow along, that's okay. Okay, because you're at the point where you have to expose yourself to lots of problems. All right, next. Find two positive numbers whose product is 100 and whose sum is a minimum. Okay, find two positive numbers whose product is 100 and whose sum is a minimum. All right, well, where would you start here? Make a formula, right? And sometimes, I mean, you guys may be at the stage where you don't need to do this anymore, but it may even be helpful to do like a let statement or assign your variables, right? And in fact, we did that in the previous problem through a diagram. As soon as we drew that diagram and wrote the width on the shorter side and the length on the longer side, we assigned variables, okay? So if you said, let the two numbers be x and y. Now you have something to work with, okay? So product is 100. Okay, so can we come up with an equation now? Yeah, okay. What would the equation be? Yeah. Yeah. Okay. The sum is a minimum. We don't know what the sum is, but we know that we want the sum, which is x plus y, to be a minimum. We want to minimize that. Okay? Now, here's what you always want to try and do. You're going to have one equation, and then you're going to have another one with too many variables. So using the first one, try and isolate a variable so that you can do a substitution like we did in the previous problem, right? So here it doesn't really matter which variable you isolate. You could isolate x or y. If I said that y equals 100 over x, for example, I could also do x equals 100 over y. Doesn't really matter because I didn't have to use x and y. I could use a and b if I wanted to. Or, I don't know, you could use a heart and a smiley face. Variables don't have to be letters. They can be any symbol you want. Okay. Now what I can do is I can take this and sub it in there. Okay. And now I want to minimize this. Okay, and I may even simplify that a little bit by coming up with a common denominator. In this case, the common denominator would be x, because this is over 1 right now, right? So if I multiply this by x over x, I'm going to get x squared plus 100 over x. Okay, so if I want to minimize this, again, the minimum is going to be where the derivative is equal to 0. Okay, so if I find the derivative of the sum, okay, or it may, I mean, it's not necessarily, it could also be a maximum point. But if we look for those critical numbers of the derivative, then we have some test values that we could take, right? And that's what we learned from the first derivative test. Okay, so if I take the derivative of the sign, I now have something to work with. Okay, so that's what I'm going to do. So if I here take the derivative, to see where the sum is at a minimum point. You may, in this process, also find maximum points that way, okay? That's okay. We're just right now interested in the minimum point, okay? Now this here is a quotient rule, right? So to get this, the sort of, I'm not leaving myself a lot of room here, but I'll do it on the next line. Maybe I'll do this, S prime. There we go. Okay, so I need to go U prime V. Well, U prime, that's the numerator prime is 2x, times V is the denominator, times x, minus UV prime. U is x squared plus 100, times V prime is 1 over V squared. Okay, so what I end up with here is 2x squared minus x squared minus 100. So in the numerator, that's going to give me x squared minus 100 over x squared. Okay, now in terms of the critical numbers, I end up from the numerator with the critical numbers of, if I solved this for 0, right? Then I'm going to get x squared equals 100 and x equals plus or minus 10. Okay. Now, we also have to go back and make sure that we pay attention. We have to be positive. So in this case, x has to equal 10. Okay. Y is going to equal 100 over x, which is 100 over 10. Which is also 10. Okay? So the two numbers are 10 and 10. Now, you also do have another critical number of 0 from the denominator. But if x equals 0, then you're not going to get anything that has a product of 100, right? So that is a critical point in the derivative, but it's not a max or a min point. Okay? Yeah, so our two numbers are 10 and 10. Okay? If we didn't have the requirement that they had to be positive, then there would be two solutions, 10 and negative 10 and negative 10. But if we have the requirement that they have to be positive, then the two numbers have to be 10 and 10. Okay. Questions with that one? All right, you ready for the next one? Okay, the next few, they're a bit of a doozy. But again, this is all about exposure. Okay, so find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Okay, so this is a parabola that goes sideways, right? Because it's the inverse of x squared equals 2y, or y equals x squared over 2, right? So this is going to look like this, roughly. I don't have to be too precise here, but there we go. Okay, and then we've got this point 1, 4. And essentially, what we want to know is, what is the point on this parabola that has the closest distance? Okay, so we're looking for this point xy. That's what we want to know. Okay, have you guys learned the distance formula between 2 points? No? Okay, that's okay. It's all good. Okay, now, one thing I want to point out, that when you're looking at the shortest distance between 2 points, it'll always be perpendicular, right? You're never going to go this way. You're always going to take the hypotenuse. Okay, so these are going to kind of be, this is going to be perpendicular. Okay, now if I kind of just extract this over here a little bit, okay, I've got this point, I'm going to take the parabola out of it. I've got this point over here, 1, 4, and then I've got this point over here, x, y. And I want to know what that is. Okay, now this over here is x, this over here is y. Okay, this is what we want to know right here. We want to know that distance. The parabola, when you have the parabola in the picture, it can kind of make things a little confusing. I could draw that same triangle in here if you want, but it gets a little bit, the diagram gets a little crowded. Okay, but basically this is that same point over there. It's still on the parabola. I could still draw that in, and maybe I will after. But I'm just trying to show you where we're going to come up with an equation that's going to help us to find that value d. Okay, and this, as you may guess, is going to come through Pythagoras because I've got a right triangle there. Okay, now if this over here is 1, doesn't actually look, hold on, I gotta fix this a little bit because it's a little off. Let me make it a little bit more accurate, just a little bit. Doesn't have to be perfect, but even to my eye, this is like not close enough. Okay. So this is 1, 4. There's the point. And then we've got this. Oh, wait, I wasn't going to draw that in. Whoops. Okay. Okay. And then I've got this point, xy. Okay. So this over here is x. This over here is y. And now I've got like a right triangle. This is my distance right here. And that's really what I want to minimize. Okay? Here, though, I've got this right triangle. So if I call that A and that B, then I can write an expression or write an equation using Pythagorean theorem that relates A, B, and D. Right? I know that A squared plus B squared equals D squared. Okay? I don't want A and B, though. I want X and Y. So what I need to do is figure out, well, what is B in terms of X and Y? If this is 1 and this is X, how much is just this part? Because that's what B is. So this whole piece is X, and that chunk is 1. How much is this piece is 1? How much is just that part? Yeah. Yeah, you could think of it that way, right? 1 plus b equals x. So what's b going to equal? X minus 1. Yeah, b is x minus 1. Okay, so I'm going to replace this with x minus 1 squared. Okay, now this is y, and this is 4, and this is a. So that's actually, Arya, that's a great way of thinking of it. Y plus a equals 4. If y plus a equals 4, what is just the a equal to? What's a equal to? Yeah. Okay, so this all got a little crowded. But this piece, let me just actually rewrite this down here, is going to become, if a is 4 minus y, then instead of a squared, I'm going to have 4 minus y squared. Okay? Instead of b squared, I'm going to have 4 minus x squared. No, x minus 1. Thank you. There we go. Equals d squared. Okay, now this is looking a lot better, getting a lot closer. Because now I have this equation that relates this distance that I want to minimize to the point x and y. Okay? The only problem is that I have too many variables. I've got 3 variables here, and I only want 2. Because if I have 2 variables, I can take a derivative, find out where that derivative is 0, right? And then I can find the exact point. Okay? So what I haven't used yet is I haven't used the fact that this point, xy, lies on that curve. So I actually do have a relationship between x and y. Okay? Y squared equals 2x. So I could actually solve for y, or I could solve for x. Okay, now if I solve for y, that's going to get a little dicey because I'm going to have to take square roots, and I'm going to have a positive and a negative. So what I'm going to do instead is I'm going to solve for x. I'm going to isolate x. Okay, so here, since y squared equals 2x, if I divide both by 2, x equals y squared over 2. And what I can do now is take this and sub it in there. And now I only have 2 variables. Okay, so all together, my equation that I want to find the minimum of, the minimum distance, is this. Let's make that a thinner line. D squared equals 4 minus y squared plus y squared over 2 minus 1 squared. Because I can replace the x with y squared over 2. Okay, and now I have a relationship between my distance that I want to minimize and 1 variable. Okay, now here's where it gets even a little bit dicier, and that is that this is a d squared. It's not a d, right? So you may think, okay, we got to take the whole square root of this thing and then find the derivative of that. And you can, but in fact you don't have to. And the reason is, what's that?
Can we take the square root at the end?
No, it's not that you can take the square root of the end. It's that the minimum of d squared is going to be the same of the minimum of d. If you minimize d squared, you're also going to minimize d. Therefore, I don't have to take the square root of that. I can take the derivative of d squared. Treat this as another variable. Treat this as an entire variable. And just take the derivative of that, and then just derive this whole side. And I'm still, all that I'm really after is what value of y makes this a minimum. That's it. So if that's all I want to know, I just need to know where is d squared at a minimum, because it's going to be the same as where d is at a minimum. Okay? So the minimum of d squared is the same, or I should say has the same y value as the minimum of d. It's not the same, but it has the same. Okay, so here's what I'm going to do. I'm just going to minimize, oh, sorry, there should be a squared there. And this, what am I doing? I'm making all, you guys, I'm making all sorts of mistakes, you guys, okay. I'm not blaming you, I shouldn't blame you. I'm like blaming you guys for my mistakes. This should be 4 minus y squared, that's better. I had the squared on the inside instead of on the outside. Okay, that's better. Okay, so to be able to find this value of y, I can just do this. Treat this as a variable and just take the derivative of that. We don't have to isolate it because it's going to have the same, we're not actually after what is the derivative of d. We don't care about that. What we care about is what's the y value that minimizes the distance. And minimizing the distance is the same as minimizing the square of the distance. Okay? So if we minimize that, well, if we take the derivative of this, we're going to have 2 times 4 minus y times, this is a chain rule, so times -1, because the derivative of 4 minus y is -1. Okay? Plus 2 times y squared over 2 minus 1 times the derivative of this, which is 2y over 2. Okay, and actually these 2's cancel. So if we do some expansion here, we're going to get, this becomes -2 times 4 minus y, and then plus 2y times y squared over 2 minus 1. And then I can keep going. So I'm going to have -8 plus y, oh no, plus 2y, thank you. And then plus y cubed, because the 2's will cancel. And then minus 2y. And that is basically d squared prime. It's not the derivative of d, it's the derivative of d squared. Yeah?
Can't you cancel the positive 2y with the negative?
Exactly. Yep. These cancel each other out. Okay? So if I want to figure out where this is at a minimum, I just set the derivative of d squared equal to 0 and solve for y. Okay, so to get the min, I'm going to make this 0. Okay, and I'll get 8 equals y cubed, which means if I take the cube root, oh, wait a second, what am I doing? y equals 2. That's better. Okay. Now we're not just after y, we want x as well. And so we have to figure that out too. Okay. Now x was equal to y squared over 2. That's what we subbed in, right? So when y equals 2, x is going to be 2 squared over 2, which is 4 over 2, which is 2. So if we want to know what point on that parabola is closest to the point 1, 4, the point would be two, 2. Yeah.
Can you just like explain one more time why d is the same as the min value of d squared? Like why is
So it's not that the min value of d squared is the same as the min value of d, right? If the min value of d is 5, the min value of d squared is going to be 25. Those two are not the same. What is the same is that the y value, the xy value that makes d a minimum is going to be the same xy value that makes d squared a minimum. And so we don't actually have to take the derivative of d. We can take the derivative of d squared if that's easier, because all that we care about is either finding an x-coordinate or a y-coordinate. And that x-coordinate and the y-coordinate is going to be the same, whether we're looking at the value of d or we're looking at the value of d squared, if that makes sense. Yeah? Okay. Okay. Anything else? No? Okay. I think I'm going to do one more, and then we'll save the rest for tomorrow. This is also another Pythagoras question, but in a totally, totally different type of realm. It incorporates other stuff. Okay? All right, a man launches a boat. And by the way, you may not get this diagram off to the side, so maybe, I don't know, I'm just going to cross that off. I should take it off, pretend it's not there. Okay, a man launches a boat from point A on the bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. Okay? So, I mean, I know you see this over here, so it's hard not to see it. But he's over here at point A. Point B is down here. And this is 8 kilometers. Okay? Oh, and then the river's 3 kilometers wide. We missed that as well. Okay? Now, here are the options. He could row all the way to B directly. Okay, he could row all the way to B, so he could go get into his boat and go from A to B. That's one option. Okay? Option 2, he could row directly to C and then run to B. People are like, no, I don't want to do that. Or option 3 is that he could row to some point in between. So he could row here, get off the boat here, and then run the rest of the way. Okay? Now, if he can row at 6 kilometers per hour and run at 8 kilometers per hour, where should he land to reach B as soon as possible? What should he do so that he gets there fastest? We're not going to take into account all the time that he has to spend figuring this out, because that may slow him down a little bit. What about the what? We're going to pretend the river is, well, we're going to, okay, so this 6 kilometers per hour that he rows incorporates the river current. Okay, that's a good question, though.
Okay, because if he was going from A to C, he'd have to put
Yeah. No, this is net speed. Net speed. Yeah, good question. Okay, so I'm going to call this point D. Okay. Now, it doesn't actually matter whether option A or option B, or option A or option B are fastest, because if option A or option B are fastest, all we're going to find is that if option A is fastest, D is going to be at the same point as B. Right? And option B is fastest, D is going to be at the same point as C. So I'm going to assume that point D, that magic spot, is somewhere in between. I'm going to say, okay, let's assume he rows there. And by the way, this is a nice little right triangle. That's kind of handy. And I need to somehow incorporate some variables here. Okay? So I'm going to call his I'm going to call this distance over here. Let's say that this is x. Okay, well then what would this piece be? What would this be? Correct, 8 minus x. Okay. So his distance that he runs, we have an expression in terms of x for that. Okay, that's easy. That's just 8 minus x. The running distance okay, so that's good. The rowing distance, if we want an expression for that, well, that's actually the hypotenuse, right? So if we call this rowing distance, let's call that y for now. That's our rowing distance. How are we going to be able to get an expression for y in terms of x? If I wanted to know how much is that, but not using y, using x, how would I do it? Yeah, Pythagoras. I can use Pythagoras. So I need to come up with a relationship between x, y, and 3, I suppose, right? So I can say, okay, well, y squared equals x squared plus 3 squared. And so to get y, normally y would be plus or minus the square root of x squared plus 9. But because this is a distance, it's got to be the positive, right? So okay, so this is our running distance. Our rowing distance equals, what is it? The square root of x squared plus 9. Okay, so this is good. We've got a couple of expressions here that use the same variable. That's always a good thing. We don't want to minimize distance, though. If we wanted to minimize distance, he would just take the hypotenuse. That's not what we're interested in. We're interested in time. And we also have this other thing in there, which is the speed. So let's think about the relationship between speed, distance, and time. How many people have seen this before? Put your hand up if you've seen that. Speed equal, or this little triangle? Yeah, how many people have not seen that? Okay, if you haven't seen it, it's not something that's like required knowledge, right? Yeah, you don't need to know it. Like, all you need to know is that, shh. Poor Harry. All you need to know is that speed equals distance over time, right? The reason why this triangle is kind of nice is that it's a visual tool that allows you to very easily isolate all the other variables. So speed is distance over time. time is distance over speed, and then distance is speed times time because they're at the same level. Okay? So whenever I'm doing speed, distance, time problems, I always draw that out. And I always remember speed because it's kilometers per hour, right? Distance over time. Okay. So what we want to minimize is time. And the time is distance over speed, or distance over speed. So this is going to become important, but not because we're interested in the distance, because if we divide that running distance by the running speed, which is 8, now we have an expression for the running time. And that we're very interested in. Okay, so let's actually start thinking about time here. The total time, actually maybe I'll do it this way. T total is going to equal the T time rowing plus the time running. Okay, now the time rowing, time is always your distance over your speed. So your rowing distance is the square root of x squared plus 9. What's the rowing speed? 6. The time running is the running distance, which is 8 minus x, over the running speed, which is 8. And this is an equation that relates the total time to that exact position x in between those two spots where he should park his boat. If we minimize the total time, we will find that position. So we want to minimize this. And again, we can do that by finding the derivative. Okay? So what I'm going to do first, I think, is just kind of to make things a little more simple, rewrite this by, for example, doing this. Instead of over 6, writing 1/6. And then also use fractional exponent instead of a radical there, because I know I'm going to need to deal with that. To the 1/2. And then plus, I'm going to split this up. So 8 over 8 is 1, right? And then minus x over 8 is minus 1 over 8x. Just makes it a little simpler to take the derivative. Okay? All right, here we go. T prime equals, all right, so this is going to be 1 over 6 times, I'm going to multiply by 1/2, and then x squared plus 9 to the negative 1/2, and then chain rule, so times 2x. Okay, so that's the derivative of that first term. And then the derivative of 1 is 0, so just plus 0. And then derivative of 1/8 x is just 1/8, so minus 1/8. And if I simplify this a little bit, I am going to get, well, here the 2's cancel. And so I'm going to have an x in the numerator. And this is negative exponent, so I'll bring that down. And I also have a 6 in the denominator. And then minus 1/8. All right. Where should I go next? Yeah. Right, common denominator. So between the 8 and the 6, that would be 24. Okay, so I have to multiply this by 4 over 4. Add this by 3 over 3. And then this piece I also need over here. So I also need to multiply this by x squared plus 9 to the 1/2 over x squared plus 9 to the 1/2. Okay, and then I'm going to get over 24 x squared plus 9 to the 1/2. I'm going to get in the numerator 4x minus 3 times x squared plus 9 to the 1/2. And that is the derivative. And to get a max min, I need to know when is this equal to 0. Or also where are the critical values, right? Now, in the denominator, there is no value where this is equal to 0 because x squared is always positive, or it's always greater than or equal to 0, but when you add 9 to it, it's always going to be greater than or equal to 9. So it's only going to come from the numerator, okay? So to get the critical numbers, I just have to set the numerator equal to 0. Okay, and maybe I'll bring this piece over here. Okay, and this is a bit, like I don't really like having that half there. It's not very helpful to solve for x. So how could I undo that? Remember, this is a radical. It's a square root. How can you undo a square root? Square it, yeah. So I got to square this, and I got to square this. You can't just square part of it. You got to square the whole thing. And when we square it, well, the 3 isn't in the radical. So this is going to become 3 squared, right, which is 9 times x squared plus 9 equals 4x all squared is 16x squared. And that is going to give us 9x squared plus 81 equals 16x squared. And if I subtract 9x squared from both sides, I get, what is that, 7x squared? Okay, so I'm going to just continue over here. So to get x squared isolated, I'll just divide by 7. And then if this was just an equation, the solutions would be that x equals plus or minus the square root of 81 over 7. But x represents a distance. So which one do we have to throw out? The negative one, that's right. So, and also 81 is a perfect square. So this is just going to be 9 over root 7. And that's approximately, I don't know, what is that? It's about 3 point something. 3.4. Okay, so that's where he's going to park his boat. Yeah. Say that again? Well, you could look at the denominator as well, but in this case, the denominator will never be 0. right? And also in terms of the first derivative test, right? And looking at the first derivative and critical numbers. When the first derivative is 0, you're going to get a max-min, okay? When the first derivative is undefined, you won't get a max-min there, but you may get a change in the function from increasing to decreasing or vice versa. So when we're talking about curve sketching, looking at that is very important, okay? For these types of questions, looking at the denominator is not very important. Because in fact, when the denominator is 0, that's actually undefined there, right? And so if the derivative is undefined there, we're not going to have a maximum value of the function. So we actually have to have, or a minimum value, we have to actually have a horizontal slope, which can only happen when the derivative is equal to 0. For the derivative being equal to 0, we have to look at the numerator. Okay, so critical numbers occur in the when the numerator is equal to 0 and the denominator is equal to 0, but when you get a numerator equaling 0, it means a different thing for the first derivative than when a denominator equals 0. Okay, and in fact, it's the same with the second derivative. When you have a numerator of the second derivative being 0, you have an inflection point there. Okay? When you have the denominator being 0, you won't have an inflection point there, but the concavity can still change, right? You may have a vertical asymptote. And so the concavity will change, but not because of an inflection point. It's because of a point of discontinuity. Okay? All right. So I'm going to stop there for today. Now, let me just turn this off.